Heinemann Higher, Chapter 9 on Integration, the mixed questions, 9R at the end, number 6. Find the area completely enclosed between the graphs of two functions. Now, well, what does this look like? Well, y equals x is easy because that's just a straight line, and that's an upside down parabola that's been shifted up 1. An upside down parabola that's been shifted up 1, it's a bit squint, and y equals x, which comes up through the origin at 45 degrees. So that means I need to know these 2 points of intersection if my graphs, of course it's just approximate, so there's no guarantee they're spaced in that proportion on either side. Well, to find those points of intersection, I'll need to substitute the two equations. So I'm looking for intersections. Intersections means that the two y coordinates should be the same, or substitute the two equations. 1 minus 2x squared, so bringing that over. 2x squared plus x minus 1 equals 0. Sort of seen that before, I think. So that's 2x, 1. The positive goes to the larger, so that must be the opposite, which means x equals either a half or negative 1. I'll put them in the numerical order. So negative 1 or a half. So it means that's cutting at negative 1 and that's cutting at a half. So the area here will be the area or the sum of all these area elements contained between them. And here it's quite easy to arrange your answers always to be positive by just making sure your area elements climb up by doing the top take away the bottom. The y coordinate of the top take away the y coordinate of the bottom gives these area elements positive heights. So just make sure you've got the top curve, which is the minus 2x squared, take away the bottom curve, y minus x. So my area is going to be this, and I won't need to put my absolute values because I'm making sure I'm going to have a positive amount. It's going to be from negative 1 until a half of the upper one, which is 1 minus 2x squared, take away the lower one, which is just x, dx. So it's going to be the integral from negative 1 to a half of, and unfortunately these are all negative signs, so I've got negative 2x squared, negative x plus 1 dx. And of course that's going to be exactly the same as the equation you had to find the points of intersection, because you just brought one over to the other side and effectively had a subtraction. The only difference is to obtain these positive areas, notice that that's the negatives of these values. You could just put that in. That would work as well. The only difference it would make if you put that intersection formula into here would be you'd have the negative of the answer, simply because you've got it reversed. But I'll just stick with this because this is the positive one. Top, take away bottom. Upper curve, take away lower curve. Y coordinate at the top, take away the y coordinate at the bottom, gives me a positive height for these area elements that I'm gathering up. Right, next step, integrate it. Up to 3, divide by 3. Up to 2, divide by 2. The constant goes back up to the linear, evaluate it at negative 1, evaluate it at a half. So that's going to be, I think it's just after this. We have to do the substitution first though. It's going to look messy. Negative 2/3 of a half cubed minus a half of a half squared plus the half minus evaluated to negative 1. Negative 2/3 of negative 1 cubed minus a half of negative 1 squared plus the negative 1. And then it's just a case of do that arithmetic, because that essentially is the question finished. It's just what does this bundle come to? And if you wanted to carefully type that all into your calculator, that would do. Or, I've not left myself a great deal of room, I could do some of this tedious micro arithmetic. It's virtually the same numbers as before. That 2 will cancel out one of them, just making that 3/4 or 12, so I've got negative a 12th. That's going to be minus an 1/8, that's plus a half for the first part. That's going to be, there's 4 negatives there, so that's going to be 2/3. There's the 3 there, so that's going to be still negative a half, and that's just going to be minus 1. And then it's a case of working that out, and I've run out of room. I just have to go up here. So my area is going to be working out the 2 parts. Well, that first part I'll make into 24ths. That second part I'll make into 6ths. There's no point doing these various pairings, they're just too messy. So what have we got for 24ths? That would be double it minus 2, triple it minus 3, 12 times it plus 12. Making this into 6ths, that's going to be double it 4, triple it 3, and 6 times it makes it minus 6. So over 24 and over 6. So that part's going to be the 5 away from that makes 7, and that part's going to be minus, and this part will be a negative 5, which gives me altogether a positive 12 over, what I'm talking about, which altogether gives me a positive, change that to 24th makes it 4 times that, 27 upon 24, which cancels out again to 9 upon 8. It's just a bit messy this time, so the area is 9 upon 8 square units, or if you like 1 1/8 square units. Perhaps a little bit messy. Either of those would do, but that should have been down under here. And of course the first significant part was this, finding these limits. Right, A. And so part B, same again, what's the area contained between these curves? I'll have to try and be a bit more concise this time. Well, that's a positive x squared, opposite signs means it's passing to the right, 6 means it's been lifted up, so it might not even cut, but I can see that factorises, it probably does cut, so it's cutting at 6, so it's probably coming down a bit like this. I have to deliberately spread it out, because I'm looking at this one, because that's just an ordinary quadratic sitting in the x-axis, but a double means it's sort of skinnier than it should be, so it's going to come down like this, which means the area I'm looking for is this area in here between the curves. So the first step is going to be, where does it cut? Where am I going to start and where am I going to finish integrating? So intersections. What's the intersection going to be? Well, equating the two, they're both in the form of y equals. That means 2x squared will give the same answer as x squared minus x plus 6. It's just, or just say substituting one into the other. It's the same thing. So bring it over to this side. I've got, that takes one, I've got x squared plus an x minus a 6 equals 0. Factorising that, x, 2, 3, plus to the bigger, opposite signs, which means x goes from negative 3 to 2. Just put them into numerical order. So it's going from negative 3 to 2, even though it doesn't look like that in the sketch. But that was the first part. I need to know the limits. Where do I start and where do I stop? And the other thing is I'm just going to arrange that this area is definitely positive. I know the integration is going to go from negative 3 to 2, because that's the limits of the intersecting area. And if I want to be positive, I just make sure that each of these area elements has got a positive height. And I'll get that if I start with the upper coordinate, take away the lower one. Upper curve, take away lower curve. The upper curve in this case is this one, x squared minus x plus 6, not the 2x squared. So if I make sure I've got x squared minus x plus 6, take away the 2x squared for the height part of the area element times its width dx, that'll give me positive answers and I won't need to bother with absolute value. So what have I got here then? So it's the integral from negative 3 to 2 of, and you can see that's going to be negative x squared minus x plus 6 dx. The same, but the opposite of the intersection equation, and it always will be. It's just I'd rather use this one than that one, because this will give me the positive immediately, but if I just did that one then and took the absolute value at the end, of course I get the same answer. Now what's this going to give me? Well, it's going to be up to 3, divide by 3, straight away there's that pest. Up to 2, divide by 2, lovely, more fractions. Constant, back up to linear term. Work it out at 2, and from that take away the answer at negative 3, and I'll move slightly over because that's going to spread out a little bit. So working it out at 2, I've got negative a third of 2 cubed minus a half of 2 squared plus 6 times the 2 minus negative a third of negative 3 cubed minus a half of negative 3 squared plus 6 times negative 3. That's the question finished. Apart from this piece of mega micro arithmetic, which you could just employ the services of your calculator for. However, I'll just plod through here because see the time it takes to type in all these wee bits. So what have I got? 2 cubes, that's negative, that's 8 thirds. That'll cancel out one of them, so that's just going to be minus 2 plus 12. Oh, those two bits aren't too bad. Minus, that's going to knock out one of them, and that's all going to be positive, so that's just going to be 9. And that's again going to be negative, and that's going to be 9 upon 2, and that's going to be minus the 18. And then I've got fractions, I've got whole numbers. Which will I do? I'll keep the whole numbers separate. I'll not work out the separate parts. I maybe just put the two fractions together. So for the fractions, I've got halves and thirds, so that could make sixths. So doubling it for this one, that'll be minus 16. 3 times it for this one, but notice that's positive, so that's plus 27. And then the number part's simply going to be, if I do the two parts, that bit comes to 10. Now that bit comes to -9, so it'll be plus 9. So far I've got 19 and whatever this comes to. This comes to 11 and 11/6. That'll give me another 1 to make it 20 and 5/6 units squared for the area, which means the area equals 20 and 5/6 units squared. It's just a case of being careful with this arithmetic. It's fine up to here, and then just take care with this. Use your calculator if you like. Right, 6.